This is the screencast for section 9.4, example 3. We're going to look at some limits of infinite sequences. Now, a sequence has a limit when the value of each entry approaches a specific number as the entries go on towards infinity. So your book defines that as the limit as n approaches infinity of a sub n. So as you go on entry after entry after entry, those values, if they approach a number, the sequence converges. If the limit does not exist, the sequence then diverges. So for example 3, part A, we're supposed to determine whether the sequence converges or diverges, and if it converges, we're supposed to give the limit. Well, I'm going to look at this numerically just to show you what I mean first. This first entry, 1 over 1 is 1, 1/2, 0.5, 1/3, 0.3, repeating, 1/4, 0.25, etc. And you can see these values are getting smaller and smaller and smaller, approaching 0. Now, of course, we can't do that so trivially. We have to use a limit by the definition of what was given to us in the book here. So we're going to take the limit as n approaches infinity of 1 over n. So the sequence is defined by 1 over n. What happens as our number of entries go towards infinity? Well, 1 divided by a number that gets infinitely large is going to approach 0. So we can say that this sequence converges to 0. Part B, again, looking at this numerically, we first have the entry 2, and then 1.5, and then 1.3 repeating, and then 1.25. So we can see a similar pattern to part A, but it's going to be different. It's not going to converge to 0 this time. As you may predict, it will converge to 1, but we have to show that. In this case, first coming up with an expression to define our sequence, and then taking its limit. So I can see that a sub n is going to equal n plus 1 over n. So the first entry is going to be 2 over 1, 2. The second entry will be 3 over 2, etc. So now I'll take the limit as n approaches infinity of n plus 1 over n. And that's kind of hard. Well, actually, I do know this. The degree in the numerator and the degree in the denominator are the same. If you remember that from section 2.6, I believe examples 3 through 9, we talk about n behavior of rational functions and what they approach, what those values approach. So in this case, the degree in the numerator is 1, the degree in the denominator is 1. I take the leading coefficients, and that limit is going to equal 1. So this sequence does converge to 1. Part C, an expression to define this sequence might be a sub n equals 2n, because these are just the even integers. So 2 times 1, 2, 2 times 2, 4, 2 times 3, 2 times 4, 2 times 5, etc. So I'll take the limit as n approaches infinity of 2n, and as n gets larger and larger and larger, this limit is going to be positive infinity, so this sequence diverges. Now, part D is already defined for us. A sub n is negative 1 to the nth power, so I will just start by taking the limit as n approaches infinity of negative 1 to the nth. And that's going to fluctuate actually between positive 1 and negative 1. So it doesn't have a limit of infinity. It doesn't have a limit of a specific value. Its limit actually does not exist because it will forever fluctuate between those two values. So in this case, this sequence also diverges. Then now try problem number 13. Determine whether the sequence converges or diverges. If it converges, give the limit. So first I have to come up with an expression to define this sequence. It looks like a sub 1 is 1 over 1, a sub 2 is 1 over 4, a sub 3 is 1 over 9. It looks like the n is being squared in the denominator. So that would be 1 over n squared. So I'll take the limit as n approaches infinity of 1 over n squared, and very similar to example 3 part A, that is going to converge to 0 because its limit will equal 0.